front says, yeah, Unit 9, electricity, magnetism, waves, electric guitars. This is the last part. So there was that's the right-hand rule I was just going over. Lenz's law has to do with magnetic flux. So I'm going to draw a picture of a magnet with the magnetic field. You need to get good at this really soon. Which way is the magnetic field going to go, left or right? No. It comes out of the North Pole, and it goes into the South Pole. And it spreads out like this. So this is what the field lines look like. And that's important that they spread out. And you could connect them if you want to, like that. So flux is a measure of the magnitude, mostly magnitude really, but we're going to be talking about direction passing through a given area. And I'm just going to use I'll use a flat. Let's say we're looking at this. This is a piece of paper we're looking at on edge. So if I draw the piece of paper right here, look at the number of field lines passing through it. That's flux. If I move it to here, there's more. Flux is increasing if I move this. And if I move it out here, then the flux decreases. Over here, this is a certain amount of flux. If I move that to the right, what happens to the flux? No, it increases. More lines go through. So the closer these lines are, the more of them are passing through there. If I put this really close right here, then there's even more flux. If the farther out I put it, the smaller the flux is. If I continue these out, you get to a point where hardly any field lines pass through it at all. So it's a measure of the intensity of the magnetic field, flux is. And so now you're ready for Lenz's law. This is a brain twister. A change in the magnetic flux through a conductive coil induces a current, meaning it makes a current in the coil, such that the induced current's magnetic field opposes the first change in magnetic flux. Here's an example. We've got a magnet right here. Which way is the field pointing, right or left, if that's the North Pole? Left. And that's what these bees are all about. And somebody's taken this magnet and they're shoving it into this tube that's inside this coil. So as they shove this into the tube, think about the flux going through the coil. Is the flux increasing or decreasing? Increasing. So we have a leftward field with increasing flux. So this law says that we're going to get a new field. There's going to be a new field created by this coil. It's going to become an electromagnet in response to that change. And the new field is going to oppose the change in the first. So with the other class, the thing that helped was not to think of this as a field, but think of this as a bunch of people pushing. They're pushing this way. They're pushing a car. They're pushing something. As you move this in, that increases the pushing. So we've got more leftward pushing. So how do you counteract that and keep the amount of pushing the same? Do you counteract it by new people also pushing to the left or some new people pushing to the right? Right. So what we're going to get here is a new field that's going to the right. And if I have an electric field in this coil to the right, then what has to be happening is my fingers have to be going to the right. Ugh. Fingers have to be going to the right. My fingers are going through there to the right, and my thumb's pointing down. So that's why this current is going downward. So that current corresponds to a rightward field that's counteracting this increasing leftward field.
Yeah, what's the little plus and minus at the bottom?
Right here?
Yeah.
That's a good question.
Shouldn't that be backwards? That is backwards.
Yeah. Maybe they're just right. I don't know. Yeah, that's confusing.
This is like if there's not already a current.
I don't know what they're trying to show there.
Wait, no, but
Oh, okay. So if you imagine this whole thing as a battery, I guess, if you say like what we've done is created in this coil, we've created a battery that pushes charge. It's going to push charge out through here, and it's going to go in over there. So maybe they're saying This is like going to be like the positive terminal of a battery, and that's the negative terminal of a battery. And charge is going to go in this direction from positive to negative. Got it?
Yep.
All right. So now look at this one. Actually, yeah, let's do this one.
So this is like if there's not already a charge going through the coil, it's creating.
Yeah, there's no charge going through the coil at all. There's no power source. It's just moving this magnet creates it.
And we'll never have a problem where there is a charge already in the coil.
Correct. Yeah. So right here, south is on the left. Which way is the field? To the right. So we've got a rightward field, and we're taking this magnet and moving it away from the coil. So what's happening to the flux, the number of field lines going through the coil? Decreasing. So what we have is a rightward field that's getting weaker, and we counteract that change by creating a new field. So how do you oppose a weakening of a rightward field? Do you do it by creating a new rightward field or a new leftward field? New rightward field. The rightward field is decreasing. We need more rightward field to keep it the same. That's the idea. So the field in here is going to be to the right. That's what this induced B is showing here. So again, if you stick your fingers through this thing to the right and you curl your thumb around it, your thumb's going to point this way. So here's yet another example. It's like this one except move in a different direction. Which way's the field here? No, left, because the North Pole's on the left. And is the flux increasing or decreasing if this magnet's moved away? Decreasing. So we've got a decreasing leftward field. What sort of new field is going to oppose that decreasing leftward field? A new leftward field is going to keep it all the same. And a leftward field means my fingers go through this that way, I curl around there, and the current goes like this. All right, so let's do some practice with this. So here's a permanent magnet. Here's just a ring. You know what? This might be a good time for me to show you a ring toss. A ring, not a ring toss, a ring launcher. Anybody watching this video, you can just fast forward until you see some action. Maybe for Colleen, I should do this. All right, that's good enough. Unplug the amp, plug this in. All right. Got an aluminum ring, and I'm going to put it on here. And I'm going to flip a switch, and guess what's going to happen?
It's going to go up. Wow.
Yeah.
That was cool.
So what's happening in here is as soon as I flip this, there's this coil here, and it's got alternating current. So the current's going this way, and then this way, and this way, and this way, and this way, and this way. And the key is that creates a changing magnetic field. So this is basically an electromagnet that's rapidly going from pointing that way to pointing this way, to pointing this way, to pointing this way. And as it does that, its magnetic field is changing. This thing is a coil. It's a very simple coil of conducting material. So when it senses a changing magnetic field, what's it going to do in response? Make its own magnetic field, and it does that by creating current, and the current's going to actually be going back and forth. But what you see is you can tell there's the opposing magnetic field because it pushes away and bounces up. Another demonstration of this, I'll pass this around, you can mess with it. These, we only need one little magnet. These are pretty strong little magnets. This is a copper tube. Will the magnet stick to it? No. No. And let me drop something down the tube just for purpose of demonstration. I've got a nut here. I'm going to drop it down the tube. Falls right down the tube. Now watch the magnet. It's falling very slowly. Because as the magnet starts to fall, the magnetic flux in this ring is changing. And when the flux changes, what does the ring do? Creates an opposing magnetic field. So this, like, it's being opposed in its fall by the magnetic fields that are pushing it up, and it just falls really slowly.
Can you launch the copper thing?
Yeah, I can launch the copper thing, but here, drop this down the tube and then pass it on. Just watch it go down the tube. It's kind of nice. So copper. Wait, oh, launch the copper tube. I thought this is
No.
like stick the whole. It won't fit on there. If I had a bigger copper tube. This is brass. This brass doesn't work as well. Hey, how about this? Is this one going to work? It's got a little slit right here. No, because you can't actually get current flowing around through there. There's no, you can't get a complete circuit. So this doesn't work.
What if you tape it together?
If you tape it with, what do you think? It's going to work?
Yeah. Oh, no, I meant like bend them with. I mean, like get super strong.
Bend them with tape?
Like super strong.
I think if you bent them until they touched, I don't think you'd even need tape then.
What did you touch to it?
Some tape, he wanted to know.
Just some tape?
Taping it would work.
Why would it not?
What's the largest thing you could launch off of that?
Why doesn't it work? Because in order for this to have a magnetic field, it has to have current going around. So really what's being induced is a current. And the current is creating the magnetic field. I'm talking about it backward. I'm saying that you induce a magnetic field and then you get current, but it's really the current causes the magnetic field. So
It's just proper order. What if you just left it on and then dropped it down?
if you left it on and dropped it, it would be difficult to do. And I can, okay, on and
Whoa.
just hangs there, won't go down. And it comes with a little light bulb that you can put on here that you can light up. But oh, you know what else? I should just stop that video because